Our planet is this single, incredible, interconnected system. From way out here, it looks so peaceful, right? But it's actually powered by this vast, incredibly complex engine. An engine that drives everything, from the clouds in the sky to the very decisions we make down on the ground. To really understand where we're headed, we first need to take a look under the hood.
So in this explainer, that's exactly what we're going to do. We're going to connect the dots. We're going to take a journey from the grand scale of planetary physics all the way down to the super intricate workings of the human mind to get a real handle on the forces shaping our climate future.
All right, here's the plan. First, we'll dive into the fundamental physics of Earth's climate engine. Then, we'll see how scientists use that knowledge to chart our possible futures. From there, we'll uncover a major technological tipping point with solar energy that's, get this, already happening. And finally, we'll zoom into the most complex system of all, us, and the psychology of what truly drives us to act.
Okay, first up, let's head into the engine room. To understand our climate, we have to start with its one and only power source, the sun.
The one key concept you got to know here is insolation. It's really just a fancy word for the amount of incoming solar energy that hits any given spot on Earth. And believe it or not, where that energy lands is pretty much the most important factor in how our entire climate system works.
See, because the Earth is a sphere, that energy doesn't get spread out evenly. The equator gets blasted with direct sunlight, receiving a whopping 2.5 times more solar energy than the poles. This creates this huge energy imbalance that the planet is constantly, and I mean constantly, trying to even out.
So how does it do that? Well, the simplest way is through something we all learned about in science class, convection. At the equator, all that intense heat warms up the air at the surface, which makes it less dense, and it starts to rise. As that warm air moves away, it cools, gets denser, and sinks back down. This simple little loop is the very beginning of all global air circulation.
But of course, on a massive, spinning planet, it's not quite that simple. This little convection current expands into something much, much bigger, what scientists call Hadley cells. Just think of them as two gigantic rotating belts of air, one on each side of the equator, stretching about a third of the way to the poles.
And here we can see the full picture. The system doesn't stop with just those Hadley cells. In each hemisphere, that global circulation actually breaks apart into three distinct zones. You've got the Hadley cell, the polar cell way up top, and then the Ferrel cell, which is kind of caught in the middle, just turning like a gear between the other two.
Which brings up a really good question, right? I mean, if the planet's main goal is just to move all that extra heat from the equator up to the poles, why this complicated three-part system? Why not just one giant, simple loop?
The answer is something super cool called the Coriolis effect. Put simply, because the Earth is spinning, it deflects any air that's trying to travel in a straight line from the equator to the poles, and it's that constant deflection that basically shatters what would be one giant loop into these three distinct cells in each hemisphere. So the planet's own rotation is what makes its engine so complex.
So we've got the engine. We understand how it works. But how do we know where it's taking us? Okay, let's move to our navigator's chart and see how scientists actually model the climate's future.
These predictions come from these incredibly powerful simulations, often called general circulation models. Here's the gist of how they work. Scientists create this massive 3D grid of the entire planet's oceans and atmosphere. They then add time as a fourth dimension. Then, for each tiny little box in that grid, a supercomputer solves the fundamental equations of physics for just one moment. It passes that result to all of its neighbors, and then it calculates the very next moment. This process gets repeated millions and millions of times to simulate our climate future.
Okay, but I know what you're thinking. How do we know these models are actually reliable? Well, one of the key methods is something called hindcasting. Basically, scientists plug in today's conditions and run the model backwards to predict the past. Then they can check those predictions against real, observed historical data to make sure the model is accurate. It's a really clever way to build confidence in their forecasts.
Now, to predict the future, these models need to make some assumptions about, well, us. And for that, scientists use a set of scenarios called shared socioeconomic pathways, or SSPs. The easiest way to think of these as super detailed what-if stories for the planet. What if population grows super fast? What if we transition to green energy tomorrow? Each one of these stories creates a different input, and that lets the models show us how the climate might respond to the choices we make.
And it turns out, when those models look at our possible energy choices, they are revealing something truly remarkable. We might have already passed a fundamental, irreversible turning point.
Yeah, a major study recently came to a pretty incredible conclusion. Based on current technological and economic trends alone, a global solar tipping point may have already passed. Now, the really key takeaway here is that this shift seems to be locked in by pure economics, which means it's projected to happen even without any new ambitious climate policies.
So what's driving this tipping point? It's simple: money. This chart shows what's called the levelized cost of electricity. Basically, the total price tag to build and run a power plant over its lifetime. And as you can see, in key markets around the world, solar is on track to become cheaper than coal within just a few years. It's the economics, not just policy, that's starting to favor renewables.
And the projected result of this cost advantage is, well, it's staggering. Models are showing that by 2050, solar could be responsible for 56% of all global electricity production. We're talking about a fundamental restructuring of our entire energy system here.
But, okay, let's pump the brakes for a second. This solar future isn't inevitable. There are 4 massive challenges we have to solve. How do we build grids that can handle power when the sun isn't shining? How do we finance this enormous transition all over the world? How do we make sure we have the supply chains for all the critical materials we'll need? And maybe toughest of all, how do we navigate the political resistance from industries that are going to be disrupted? And all that brings us to our final and maybe the most important piece of the puzzle. We have the physics, we have the technology, but what about us? What actually drives human beings to take action?
So what really gets people to act? A huge meta-analysis recently crunched the numbers from dozens of studies to find the answer, and the results are genuinely surprising. Just look at what's near the bottom of the list of what motivates us: lack of knowledge and personal experience with hazards. The very things we often think are the most important actually turn out to be some of the least effective.
So what actually works? Well, it boils down to 4 key things. The single most powerful motivator is seeing that other people are already doing it. That's the power of social norms. Right up there with it is feeling negative emotions, like guilt or even fear about our impact. And finally, it's a 2-part belief. We have to believe that the action itself will actually make a difference, and that we are personally capable of doing it.
This implies that some of our most common communication strategies are, well, they're fundamentally misguided. Just throwing more facts and data at people, the whole information deficit model, it doesn't work. And surprisingly, neither does relying on someone's personal experience with a climate disaster or trying to appeal to these abstract ideas like a love for your home. These things just don't translate into action as much as we think they do. And this brings us to the final critical question. The physics is clear. The technology is hitting a tipping point. And now we understand the psychology. So the real challenge in front of us is this: how do we use what we now know about human behavior to make climate action feel normal, to make it feel effective, and make it feel like something that every single one of us can truly be a part of?